Hi everyone. In this video I will be demonstrating a one-way analysis of variance using the one-way ANOVA route in SPSS, and I'm working with SPSS version 28 in this demonstration. So there is an additional feature in version 28 that was not present in earlier versions, and that is the ability to obtain an effect size measure. You can actually obtain the same effect size measure through an alternate route, but again, I'm going to be focusing in on the one-way ANOVA route. And the way that you access that in SPSS is to go through Analyze, Compare Means, and then go down to where it says one-way ANOVA. So that's a route I'm going to be focusing in on. So briefly, I do want to mention that underneath the video description you will find a link to the SPSS data file that I'll be working from in this presentation, so you can download a copy of the data to follow along. You will also find a link to a PowerPoint that will provide some additional details that you might find useful as you go through the example. So let's go ahead and get started just by considering the data that we're working from. So we have essentially fictional student data where each row in the data set, rows 1 through 30, represents a given student. And so each of the students in the data set will have received one of 3 motivational interventions. And what we're going to be doing is testing whether there are differences in the means in terms of academic motivation by motivational intervention. So the motivational intervention variable that you see right here is a categorical variable with 3 levels, and if I double click right here and go under variable view, we can just briefly take a look at the values and what they represent. So you'll notice that a value of 1 in our data set on this variable represents students who received intervention A. A value of 2 represents students who received intervention B, and then a value of 3 indicates students receiving intervention C. So our independent variable in our analysis is going to be this motivational intervention variable, and the dependent variable is academic motivation. And so this variable we're going to be treating as an interval scaled variable. So to carry out our analysis, we will go back up to Analyze, we'll go to Compare Means, and then we're going to go down to One-Way ANOVA and click on it. So this is the box that opens up. We're going to move the independent variable motivational intervention to the factor box. We'll move academic motivation to the dependent variable list. And that new feature that I was telling you about is given down here. It says estimate effect size for overall tests. And so I'm going to click this little button right here, and this is actually going to get us eta squared for our analysis, which is essentially representing the proportion of variation in the dependent variable accounted for by our independent variable, or factor variable. So now we'll also click under Post-Hocs right here. And typically what happens when you're running a one-way ANOVA is that if you find that there are significant differences among the group means, then oftentimes you will want to follow that up by testing which of those means are different from each other. So a standard set of procedures are post-hoc tests. Probably the most common post-hoc test that is utilized is Tukey's post-hoc test right here. And just keeping in mind though that this test assumes equal variances for your groups. So on the off chance that we don't have equal variances across the group, so I'm going to go ahead and click down here where it says equal variance is not assumed. I'm going to click on Tamhani's T2 right there. So we'll click on continue and then go to options, and under options we can request descriptive statistics. We can request the homogeneity of variance test. This is basically Levene's test, and one of the major assumptions of analysis of variance is that we have homogeneity of variances, or basically equality of variances. And so when that assumption is violated, then that can call into question our inferences with respect to the F-test or the ANOVA test. So we want to evaluate that assumption, so we can click on that button for homogeneity of variance test to do that. You'll notice next we have 2 other options. We have Brown-Forsyth test and Welch test that are given right here. And so these tests are essentially robust ANOVAs, if you will. And the basic idea is that if there is a violation of homogeneity of variances, these two tests right here are designed to adjust for that violation and give us a better picture about the differences in group means. So with any luck then, that they would reduce the likelihood of making a decisional error when it comes to making an inference regarding differences in population means. Then finally I'll click on means plot right here and then continue, and then we'll click on OK to generate our output. So as we're looking at our output, you'll notice the first thing we've generated are descriptive statistics, basically for each of our groups and then overall. So you'll see we have intervention A, intervention B, and intervention C that are given right here. We have our sample sizes, which are given by these n's right here. The means for each of our groups are given right here. So you can see just descriptively that the mean for intervention B is 34.5069. That's actually the highest mean in terms of academic motivation, followed by the mean for intervention C right there at 30.3497, followed by the mean for intervention A at 25.5265. You'll notice in the next column we have the standard deviations for each of our groups. We have the standard error of the mean for each of our groups, as well as 95% confidence intervals that are given right here. So all that information is available to you. We'll scroll on down a little bit further, and you'll notice that we have our analysis of variances given right here, and then you'll also see that we have that test of homogeneity of variances that's given above. So as I was noting previously, the analysis of variance, this is the test that we're using to test for differences in our group means. And so if we find that there's statistical significance with respect to this test, then we would infer that there are differences in the population means on our dependent variable. And so you'll notice right here, this is basically an F test that's given. So it's using the F distribution. And you'll see that this p-value right here under the sig column, the p-value is p less than 0.001. And so if we're using a conventional alpha level of 0.05, you can see that the p-value is less than that alpha level, which would lead us to reject the null and infer that there are differences in the population means. And just to give you something to help visualize where that F value is falling relative to the null hypothesis, there's a nice little online simulator for different types of distributions at this site right here. This is statdistributions.com, and I've gone to the page for F distribution, and I've included the degrees of freedom between and degrees of freedom within right here, and set our alpha level at 0.05. So this distribution that you see right here is the F distribution under the null hypothesis. And essentially our data, remember that the F value is 30.36. That's going to actually put our data way the heck up here in the upper tail of this distribution. So you can, if you look at the little shaded area, that is the region of rejection of the null hypothesis, and this F value right here that's given right here, this is a critical value. And so the basic idea is that if the F value from our sample data falls at that point or exceeds that point, then that would lead us to reject the null. So again, all of this area right here represents a region of rejection, leading us to reject the null and infer that there are differences among the population means. So now I'll scroll down. Oh, actually, before I do that, let's go back and look at this previous table with our test of homogeneity of variances. And again, just to reiterate, one of the main assumptions of the analysis of variance is that we have equal population variances. So this test up here of homogeneity of variances is a test of that assumption. And assuming that we can infer that the population variances are equal, then we can trust our ANOVA results a lot better. If we find evidence that there's a violation of that assumption, then in that case that kind of calls into question perhaps the validity of our interpretations with respect to our test of the mean differences. And so in some cases, if we have a violation of equal variances, that can translate into an increased probability of a type 1 error, and in some cases it can lead to an increased probability of type 2 error. So that's why we want to look at this test result that's given in this area for tests of homogeneity of variances. And so you'll notice in this version of SPSS, some of the many of the older versions only gave you essentially one Levene's test, and it was based on the mean that you see right here. And so in more recent versions, you're actually getting multiple versions of that particular test. And so you can think about this first row, the results in this first row, as essentially a test that is probably less robust to non-normality than those other tests. But I'm going to focus my attention just on interpreting that right now, just keeping in mind that these other test results may be a little bit more robust to non-normality than this one. So you can see that the p-value for this particular test right here, it's 0.099. And so if I compare that against the conventional alpha of 0.05, you can see that the p-value exceeds that 0.05 level, and that would actually lead us to not reject the null hypothesis. Now, under most circumstances, or many circumstances, when we are performing statistical tests, we're looking for rejection of the null. But in the case of testing assumptions like this, we're actually kind of looking to not reject the null. So if this p-value right here that you see is greater than the alpha level that you set, again, conventionally it's 0.05, then that would lead us to not reject the null. And the null for this test is that we have equal population variances on the dependent variable. So in this case, that this finding right here would be consistent with an assumption that that we have equal variances. So that gives us greater feeling of confidence when it comes to interpreting the results from our analysis of variance that's given right here. So when we scroll down a little bit further, you'll see that we have ANOVA effect sizes, and you'll notice that there are various effect sizes that are given. I'm going to focus on eta squared right here, and the eta squared value that you see is essentially the proportion of variation accounted for in the dependent variable by the independent variable. So just briefly, I'll kind of scroll up just a bit here, and we'll look back at our ANOVA summary table. So the eta squared value that you see right here of 0.692, this is easily calculated as a ratio of the sum of squares between groups to the sum of squares total. And you'll notice that essentially what we're doing is we're breaking down the total sum of squares in the dependent variable into two components. There's a component that is between groups, so this is where the sum of squares between would be, and then we have the sum of squares within right here. And so obviously this is kind of not matching up with what we have for our point estimate, but that's the breakdown. So that's where the sum of squares total that you see in that last row in the ANOVA table is showing up. That's this value right here. So if we take that ratio of between group variation to the totals of the sum of squares total, or basically the total variation, that's what gets us our eta squared that you see right here. So now with respect to making a judgment or a decision about what that really means, we might consult Cohen's benchmarks from 1988 regarding how to interpret the magnitude of the effect of the independent variable on the dependent variable. So by his conventions, he suggested benchmarks of 0.01 for eta squared as indicating a small effect. A value of 0.06 would be an indicator of a medium effect, and then a value of 0.14 would be an indicator of a large effect. So you can see right here that our value is 0.692. So that using that set of benchmarks right there, we would interpret this to mean that the independent variable is having a large effect with respect to the dependent variable. Now, another thing that is included in this portion of the output is a 95% confidence interval right here. So it's giving you a lower bound and an upper bound for that eta squared value. So the lower bound is 0.436, the upper bound is 0.788. And you can see right there that the lower and the upper bounds, but those are clearly well above the 0.14. So even using the confidence interval right there, you can see that the estimated effect would be considered large. Now when I scroll down a little bit further, you'll see that we've got some more output. You'll see that we've got this robust test of equality of means, and then you'll see next we've got multiple comparisons. So what I thought I would do is before I get into the robust test right here, I'm going to go ahead and look at the Tukey's results that are given in the multiple comparisons table, because basically after you've rejected the null concerning the equality of the group means, if I reject the null and I infer that the group means are different, then I may want to kind of explore which of those group means are different. And so that's where I might use post-hoc tests, where in this case I'm looking at pairwise differences in the means. And so when I use the term pairwise, I'm referring to basically a comparison involving two means during a given comparison. So as you can see right here, this multiple comparisons table is broken out into two sections. There's Tukey's HSD and Tamhani's T2 tests. And so as I mentioned before, the Tukey's is used in those cases where you have the assumption of equal variances. The Tamhani's T2 is used in those cases where there's no assumption of equal variances. So I'm going to be focusing right now, because we've assumed that we have equal variances, I'm going to be focusing on Tukey's HSD. And so as we're looking at this table, you'll notice over here you'll see two columns. You'll see column I and column J, and I and J are just denoting the groups that are involved in a given comparison. So you'll see we have intervention A and intervention B, and then intervention A and intervention C right here. So in this first portion of the table, we have comparisons between group A and group B and group A and group C. So in the first row in our output right here, you'll see it says mean difference I minus J. So what's going on right here is this value is computed by taking the mean on A and subtracting the mean on B. And you'll notice that this value right here is negative. And basically what that's telling us is that the mean for group B is actually 8.98 points higher than the mean for group A. And if we look in the sig column right here, you can see that the p-value, we would describe that as less than 0.001. So we would in effect determine that, or make the judgment that we are going to reject the null of equality of group means and infer that yes, that there is a difference in means between these two groups. Then when we look at the comparison between A and C, you can see that we have our mean difference that's given. So the mean of A minus the mean for C equals negative 4.82326. And what that's telling us, because again that number is negative, that's actually telling us that the mean for group C is 4.82 points higher than the mean for group A. And you can see, given the p-value, that this difference is also statistically significant. Then you'll notice that we have intervention B, and we have a comparison with intervention A and intervention C. Well, we've already tested for the difference between A and B, so there's no need to go here, right here, and then try to look at that test, because we already have done that above. So we won't bother with looking at that right there. Instead, we'll just look at B versus C. So there's intervention C right there. So if I take the mean for B, subtract the mean for C, then in this case you can see that the difference in means is 4.157, and because that value is positive, that's telling me that the mean for B is greater than the mean for C, and you can see that that difference is also statistically significant right here. The remaining comparisons that you see down here involving intervention C are redundant with the comparisons that we computed above. So there's no need to go any further with respect to those comparisons. We only have 3 comparisons that we needed to carry out and to test for differences in means. So next, we'll go back up to the robust test of equality of means. And as I mentioned before, we had determined that or decided that we have substantial or reasonable evidence that we have equal variances in the population on our measure of academic motivation. But if had that assumption been violated, then we might consider going down here to the robust test of equality of means and using them as a basis for our inference concerning the differences in population means. So although we don't really need to do that in this particular case, I'm going to go ahead and just briefly talk through these results. So you can see that, again, these are robust tests. These are essentially adjusted one-way ANOVAs to minimize the effects of any kind of violation on our inference. And so you can see right here that with respect to the Welch test, you see that it is statistically significant, and you can also see with respect to the Brown-Forsyth test that we have statistical significance. So in both of these cases, these would be leading us to infer that there are indeed significant differences among our group means. And so given that, then what I might do as a follow-up is to go down here to where it says Tamhani's T2 test, and essentially just use the same process that I'd used above with respect to Tukey's. You'll notice that the mean differences that are given in this column right here, these are all the same as what was given above. You'll notice though that the standard errors look different, and so as a result, we have adjustments to our test. And you can see with respect to the p-values some differences. For instance, if we look at the difference between intervention A and intervention C right here, there's p-value for that test is 0.004, still less than 0.05, but you'll notice that that value is different than the one that we saw with Tukey's up above. You can also see in terms of the comparison between intervention B and intervention C right here that we have a p-value that's equal to 0.007, and that's clearly a little bit different than what we had above with respect to Tukey's. So at any rate, that Tamhani's T2 test is useful in those cases where we have potential evidence of a violation of that homogeneity of variance assumption. One other thing to kind of note in the output right here for the multiple comparisons, there is a column or a couple of columns right here for the 95% confidence interval. This is basically giving us a lower bound and an upper bound for the differences in means. And so sometimes folks choose to utilize the confidence intervals for hypothesis testing. So the basic idea is that if the null of 0 falls between the lower and the upper bound, then in that case we would conclude that there's no difference in means, and if 0 falls outside of the lower and the upper bound for a given interval, then we would infer that there is a difference in means. I'll be honest, there's not really a whole lot of point in going about it from that standpoint, since you have this column of p-values that are given right here. We'll scroll on down a little bit further, and the last thing I'll show you is that we have a means plot. So this is just, unsurprisingly, it's a plot of the group mean. So there's the mean for intervention A, the mean for intervention B, and the mean for intervention C right here. And so it just kind of gives you a little bit of a visualization of the differences in means. And the lines are just basically connecting those the means that are adjacent to one another.